you must find what you like, because the world advances and you can't know now what good can come out of what you like, but you know that you'll enjoy it and do a good job. I was finding my way in this wonderful, interesting, exciting world of physics.
Pauline Morrow grew up in rural Mexico, the daughter of educational missionaries. Though she received little formal schooling, she applied to and attended Wilson College for mathematics.
I had not been in the physics class more than about a week or two that I really recognized something that I really, really liked. So I decided that was what I wanted.
Encouraged by her lifetime mentor at Wilson College, Dorothy Weeks, the first woman to earn a PhD in mathematics at MIT, Pauline pursued her love of physics and set her sights on graduate school at MIT.
She was the one that said, MIT, that is the place for you to go, because she knew that I would feel at home and as if I belonged. And I did. It worked well.
Pauline arrived at MIT in 1939 to begin her PhD. She hoped to study cosmic rays using an early digital computer called a differential analyzer, under the instruction of Julius A. Stratton, professor of electromagnetic theory and later president of MIT. But World War II intervened.
Just about the time that I was ready to think about doing a thesis, they said that the differential analyzer could not be used for any subjects except defense work. So Professor Stratton asked if I would be interested in doing a thesis in electromagnetic theory instead.
Much remained unknown about how electromagnetic waves travel through Earth's atmosphere, and that's what Pauline set out to understand in her thesis. That foundation in the theory of electromagnetic waves, be they radio waves or microwaves, would serve her throughout her career.
Meanwhile, I had met and dated and become engaged and married to my husband, and he was in meteorology.
A fellow MIT graduate student, James Murdoch Austin, received his degree in 1941, and the young couple was married that summer. He then took on a professorship in meteorology at the Institute and became a leading expert on air pollution. James was always supportive of Pauline's work and family balance, and the two collaborated on many projects throughout their careers.
I was interested in what I was doing, and I wanted to proceed ahead. My husband recognized that, so it worked out very well.
Pauline Morrow Austin completed her thesis in 1942 and was immediately hired for defense work at MIT's radiation laboratory. That year, the New York Times lauded her as one of the top female scholars aiding the war effort. During its time, the Rad Lab employed 3,500 staff and developed over 100 radar systems.
At first, I was working on the low-rand navigation system because that was most connected with what I had been doing with Professor Stratton. Then I was put in the antenna group, and that had to do more directly with the radar.
Although radar was being developed to search for aircraft, it quickly became apparent that it had meteorological applications as well. Weather patterns could also be tracked and studied. This emerging use led to a post-war opportunity for Austin, MIT's new weather radar research project, which focused on detecting rainfall using radar signals. A meeting was convened between MIT and the Army Signal Corps to discuss radar's potential.
And then somebody said, how about electromagnetic theory? And they said, yes, they thought they'd need a full-time man on electromagnetic theory. So I said, well, would you consider a half-time woman? And I went on to that project in 1946.
Radar works by sending out short, high-powered pulses of microwave radiation that are focused into a narrow beam by a large antenna. When these pulses encounter a large collection of raindrops, they are reflected and scattered, and some of that radiation bounces back and is detected as a radar echo. Starting with early film images, Austin's research attempted to quantify rainfall and understand its microphysics using radar.
I am doing some comparisons between the radar measurements and surface rain gauge measurements to see whether we can get a little bit more accurate rainfall amounts out of the radar. The radar gives the distribution, but it's not that good at giving the actual amounts. You're looking at a volume of space with a bunch of raindrops or snowflakes all moving around, so you have a fluctuating signal, and you have to average it. That was a very, very difficult thing in the early days before we had computers that could handle it.
Beginning in 1948, her husband James began a weather forecasting segment on local WBZ TV. To illustrate the reports, Austin provided the earliest radar images to appear on TV, bringing radar into the home for the first time.
You know, nowadays you see on TV the weather coming and going. Well, all of that was not possible.
With the help of Alan Bemis, an MIT professor of physics and the first director of the Weather Radar Research Project, Austin dedicated much of her life to understanding a radar feature called the bright band, a narrow horizontal layer of intense radar reflectivity in the atmosphere where snow melts to form rain. Understanding the microphysics behind this phenomenon has helped to establish standards to classify local storms.
When we first started the radar lab, we couldn't leave the radar going on its own. Somebody had to be there and change the films and do all this. So if there was a big storm going on, we'd have to set it up and have somebody around the clock.
Austin worked long hours, often splitting her time between caring for her husband and 2 daughters and opting to work the graveyard shift. In 1956, Austin took over the project and served as director until her retirement in 1979.
When I applied for the job in the Weather Radar Project and they gave it to me, I couldn't believe it that somebody would actually pay me to do what I really like to do.
Austin oversaw the installation of the S-band radar on top of the Green Building. Working with Spiros Giotis, a prominent project engineer and lifelong collaborator, she continually pushed for improvements in measurements of rainfall intensity. Austin helped pioneer many changes in her field throughout her long career, which included international collaborations and the introduction of digital data, with projects like the first observing phase of the Global Atlantic Tropical Experiment, or GATE.
In the early 1970s, actually it was in 1974, there was an international project to study tropical convective showers because they are extremely important to the general circulation of the atmosphere. We just decided that it had to be digital data if we were going to find out about those convective showers.
Even after her retirement in 1979, Austin couldn't stay away from MIT, analyzing new data to push toward a better physical understanding of radar echoes.
When I retired, I was just beginning to be able to get my hands on digital data after looking at films for decades. So that's why I still keep on coming in and looking at data.
Aided by technological advances, Austin and her colleagues in MIT's Weather Radar Research Project made great strides to understand observed meteorological phenomena. Some of their most notable achievements include making accurate and quantifiable measurements of weather radar echoes, as well as deciphering and dissecting specific meteorological information contained within these echoes. But Austin's contributions to the field and her love of radar research extended beyond her years, influencing generations of scientists to come. It is estimated that in the first 40 years of the Weather Radar Research Project, well over 200 people from all parts of the world and all stages of study participated in various project activities. Today, they and their students are touched by Austin's remarkable life and dedication to her field as they move forward into the frontiers of science.
I think I have been very fortunate because I have had a very good life. I had a good family, and it has been simply, if a door of opportunity opens, you walk through it. You go ahead and try to recognize what it is that gives you satisfaction and do it.